Okay, welcome everyone to today's webinar. Again, the topic of our webinar today is high fidelity, high productivity safety simulations of airflow over a golf club head. This is a collaborative webinar between some researchers at University of Tennessee, Chattanooga, here at Pointwise on the pre-processing side, and FieldView on the post-processing side. So my name is Chris Sidoroff. I'll be your host today. Before we kind of get into the introductions here, I just thought we'd go over a little bit of the ground rules. So what we're going to do is we're just going to have, we're going to go through our presentation. It'll probably take approximately 30 to 35 minutes. At the end of that, we're going to open up the floor to a question session, which I will moderate. Also, during the webinar, if you have questions, you can type them in the question and answer window, and I'll be the one that answering those ones during the webinar. So I'll do my best to answer them when I get some time, and if not, we'll answer them verbally at the end. So let's get started here. So just some introduction about the presenters and panelists today. We have Steve Carman and Bruce Hilbert from the University of Tennessee, Chattanooga. Steve received his bachelor's and master's in aerospace engineering from Texas A&M and his PhD in aerospace engineering from the University of Texas at Arlington. He was actually employed at Lockheed Martin Aerodynamics here in Fort Worth between 1983 and 2003, and since 2003 he's been a professor at the University of Tennessee at Chattanooga at the SimCenter, National Center for Computational Engineering, and his area of research and specialty is in mesh generation. He's going to talk about some of that stuff today. Bruce works alongside Steve there. He's been the primary grid generator at UTC SimCenter for about 3 years. He's been involved in a wide range of projects, including aircraft, turbomachinery, watercraft, fuel cells, and waveguides. And he's also engaged in active research regarding tetrahedral meshing and grid procedures involving CAD modeling. And before his tenure at the SimCenter, he was an associate professor of mathematics at Chattanooga State Technical Community College for about 10 years. Representing Intelligent Light, we have Yves-Marie Lefebvre. He's a sales and support engineer from IL. He was a CFD engineer for about 6 years prior to joining them, working on a variety of aerospace, automotive, and marine projects. And he joined Intelligent Light in 2007. He has a degree in engineering degree in numerical simulation from the Institut National Polytechnique de Grenoble from 2001. And then myself, Chris, here at Sidoroff at Pointwise. I joined the company in the fall of 2007. I'm a technical sales engineer. I have a BS and an MS from mechanical engineering at the University of Alberta in Canada, and I received my PhD a couple of years ago from the mechanical engineering department at Syracuse University. And I have a variety of past industrial experience in a variety of fields, including the petroleum and aerospace engineering industries. So before I turn things over to Steve and Bruce, I'm just going to give a brief agenda of what we're going to be covering today. We're going to give a little background and motivation for the study. Most of the pre-processing is going to be discussed by Steve and Bruce, but I'm going to give a little bit more background on some of the pre-processing stuff that they're going to show in Pointwise. Then Steve and Bruce are actually going to talk about their own mesh generator called VMesh, which stands for Voxel Mesh Generator. Kind of interesting. And then they're going to go through the solver and problem setup, and then they're going to pass controls over to Yves-Marie, and he's actually going to go over the post-processing that they used with FieldView to deal with these large CFD problems. And then when we're done, we'll leave lots of time for a question and answer session. So with that, I'm going to pass things over to Steve and Bruce.
Okay, for today, for this webinar, we wanted to choose a case that was applicable to the general population. There wasn't any restrictions on the geometry or anything like that. We want to show the complete CFD process from geometry creation through solution post-processing. So we're going to do flow over a golf club head. And we're going to show steady and unsteady CFD results computed on a distributed memory Linux compute cluster with our in-house code called TENASI. The solver is not the focus of this presentation, but it's an integral part, so we'll briefly mention it and describe the method. And then we'll turn over control to Yves-Marie to have him show you how you can use the results from this and post-process with FieldView. So this webinar will illustrate the various steps of a complete CFD process that is typically followed for aerodynamic analyses of realistic geometries.
Okay, thanks, Steve. Steve's gonna get back here in a minute. He's gonna talk about that process, but what I'm gonna do is just give you a little segue on some of the techniques that that they're gonna talk about. So the first one is a hybrid meshing technique that we call T-Rex. So this is concerned with creating boundary layer meshes. So the typical traditional approach for doing unstructured boundary layer meshes, is to create these stacks of extruded prisms where you start with a triangulated surface mesh and then you create these layers of triangular prisms. These traditional approaches, a bit of a drawback to them is that most of them, if you encounter a single point advancement failure, it'll actually cause the entire extrusion to stop. And so, I mean, the drawback to this is that you rarely ever get very full layers of boundary layer cells on complex geometries. You may be restricted to maybe 2 or 3, or maybe at the most 5 layers, but when really you would like to have about 20 or 30. So all alternative to this meshing strategy is what we call T-Rex, and it stands for anisotropic tetrahedral extrusion. And so it actually removes that drawback from the traditional approaches where single point advancement failure does not cause the extrusion to completely stop. It only stops the extrusion locally. It actually allows it to continue elsewhere. And in my next slide here, I'm going to show you a picture kind of highlighting when I talk about that. So then when it's done creating these layers of high aspect ratio right angle tets, it fills the void in with remaining isotropic tets. And the idea, again, by creating full layers is you get a much smoother transition into the free stream region. And then as a post-processing step, you actually have the ability to go ahead and merge these anisotropic tets back into prisms when they're done, because most flow solvers will like the prisms. They'll result in a much better cell. So here's an example mesh that I had done just to illustrate what I was talking about. So this is an exhaust port valve in the actual flow passage. So over here on the left, I'm just kind of indicating where we have full layers. Full layers can grow where there's room, so they grow all the way out, and then they kind of merge together with this isotropic region, and we get a very smooth blending. But also, you notice down here in this very small gap where the lip of the valve is coming close to the valve seat, there's actually not very much room, and so the layers are going to stop. They have to stop prematurely because there's just not enough room to grow those full layers, and T-Rex handles these collisions automatically. So again, the single point advancement failure does not prevent the growth of layers elsewhere. And then I mentioned the prism merging. So this is the picture on the left is showing what the actual T-Rex mesh is going to look like. We have these stacks of right angle, high aspect ratio tets that are growing normally off the surface. And so that method is what gives T-Rex its flexibility. And then again, I mentioned this second step, this post-processing step, where you can tell it to recombine the prism, the tets back into prisms. So we get these right angle faces in the streamwise direction. This is what most flow solvers prefer. So T-Rex itself is actually currently in Gridgen. I think Bruce is going to mention that he used Gridgen for creating the T-Rex mesh. But actually, T-Rex is coming to the next major release of Pointwise, which we're planning on getting out here early in the new year. So you can definitely look forward to some future webinars. We'll be talking about using T-Rex in Pointwise. So just the last slide, a little bit more generic one that I think that really shows maybe some of the power of Pointwise that Bruce and Steve leverage heavily for the work they did here today, is that Pointwise is actually a really flexible pre-processing tool, and I really want to emphasize pre-processing. It does more than just mesh generation. It's a tool for doing basically CAE pre-processing. So there's all sorts of ways to get your data in and out and create data and stuff like that. So on the left here we have a variety of formats that Pointwise can import. As of today, the production release of Pointwise, the best native CAD format that it imports is IGES. The next major release of Pointwise will enable some more popular native CAD formats that I've shown here, as well as getting your mesh out to your CFD solver. So all the major commercial formats, as well as a whole host of others. And I think I did a quick count. I think there's 44 total CFD solvers that we support, and that includes writing out the mesh in the native format, as well as the boundary conditions and volume conditions if they support that. And then neutral formats, which I think Bruce and Steve use, is getting, Pointwise doesn't know, you don't always have to use all the meshing techniques in Pointwise. You can maybe use a portion of it. You can maybe have your surface mesh generated in some other process and use our software to create a volume mesh. Or in the case you're going to see today, it's the exact opposite, that they're going to, excuse me, that's actually what they're going to show today, is starting with the surface mesh and using their volume mesh generator. And then we have a scripting language called Glyph that allows you to automate some of these processes and generate your own data. So with that, I'm going to turn things over to Steve and Bruce, and they're going to describe how Pointwise was used and also the solver setup.
All right, what I'm going to talk about right now is how the geometry itself was created. We got the surface as, from a kind of a one-off 3D laser scan from a vendor that came for a demonstration. And it was not very good. Lots of holes, poor scan quality, not a complete geometry. So when I brought it into Pointwise, I had to do a good deal of cleanup. And fortunately, there are plenty of tools for that in Pointwise. I was able to make a patch between the golf club head itself, that you see there in blue, and the nominal shaft. After that, creating a grid on a surface was, very easy, very straightforward. And then the volume mesh was also very easy, and used a combination of structured blocks to capture vorticity wakes off the back of the club, as well as GridGen's T-Rex algorithm to create the viscous layering necessary. Alternately, we have used this surface mesh in our own meshing technique called voxel mesh, and we still need Pointwise for that process because we need the surface mesh, and then afterward we need to read our voxel front, which Steve will talk about later, back into Pointwise to create a tetrahedral stitching layer between the volume mesh that Steve has created and the surface mesh as it was. So let me pull over to Pointwise very quickly and show you in a little more detail what I'm talking about. You can see that right here in the golf club surface itself, there were lots of anomalies. And this was after extensive cleanup in the pre-processing of the laser scan. So all I had to do was make a nice little patch, and that was accomplished with actually a structured mesh, which are fairly simple to turn into database elements, into geometry itself. And then after that, we have a complete, nice, tight geometry on which we can put a very easy, very simple surface mesh. And you can see that for the most part, I just allow Pointwise to take the patch that was read in and just mesh on those little patches. There were a few places where I got creative and decided to merge the parts of the grids together, but that really wasn't necessary. And then finally, as I said, we create the structured blocks. Again, those are to capture some vorticity. And after taking this block to GridGen, we made the block. We were able to make these anisotropic cells, if I can get it to cooperate. Here we go. That you can see form a very, very nice boundary layer. out to 20, 30 layers at worst. So that was pretty good. All right, so Steve's going to talk about how the voxel mesh was generated.
So we take the surface triangulation that Bruce just showed you and export that as an XPatch file. That's one of the formats that Chris had mentioned. And we wrote a code called voxel mesh, and it is a hierarchical Cartesian meshing algorithm, basically. I have a lot of history in this area of meshing, and these meshes have a nice feature that they're hex elements mostly, which we've learned over the years that tetrahedral elements are very dissipative with respect to vortices. And if we want to capture vortices, then we end up either generating a hex block like Bruce did in the case of the all pointwise mesh, or we can use this new scheme called voxel mesh. So we want to do a Cartesian aligned or hexahedral elements for the majority of the domain. We like to have the surface mesh defined in Pointwise, and it has some adaptation capability which we're not taking advantage of in today's webinar. So our approach is to combine the two technologies. Pointwise will be used to do the surface triangulation. vMesh will create the volume mesh from the Pointwise surface triangles. It will export a front that will be read back into Pointwise, and we'll use the ISO tet mesher in Pointwise to stitch the two together. This slide shows that basic process. On the left side, on the upper left, you see the voxel mesh that is created. It's a polyhedral mesh. In other words, it's hexahedral shaped elements, but they're not always just 6 faces. Sometimes there's subfaces and so on. So I store it as a polyhedral mesh. And you'll notice that it quits just before the surface mesh. So the volume mesh is created everywhere, including inside the body, and then it will go back and detect which elements are intersected by the geometry or outside the computational domain and remove them. Our flow solver does not fully support this type of polyhedral mesh, so we then convert to the standard 4 types of mesh elements: hexes, pyramids, prisms, and tets, and that's what you see in the lower left. The front of that voxel mesh, in other words, the quad faces that are just above the surface, are converted to triangles and exported as an XPatch file, and that is read into Pointwise. And on the upper right, you'll see that surface just above the sphere in the Pointwise window. So I will then make a tetrahedral block out of that surface and the true surface. And then we'll just use the standard parameters in the grid solve for initializing that TED block. And you can see in the middle bottom, the surface of the sphere, the triangles are in cyan, and they slice through the little TED block is in green. So then we take and combine those two meshes, the voxel mesh and that little TED block, and we get a hex-dominant, point-to-point matched hybrid mesh using the surface-defined elements. We have in-house another code called PVLI, which stands for Parallel Viscous Layer Insertion, and it can take and insert viscous layers in an existing mesh. And it uses the linear elastic relations to do this. It pushes the existing mesh out of the way, making room for however many viscous elements that you want. And it will actually measure how much space is there to determine how many layers it can insert. It doesn't have to insert 21 layers everywhere. It can insert variable number of layers depending on the space in the existing mesh. And it uses geometric progression to distribute the points in the normal direction. And here are the equations that PVLI will use. This is the 2D form of the structural dynamics equations. And typically Young's modulus is the stiffness of material, and we will compute a value of Young's modulus that is proportional to the element aspect ratio and or the inverse of the element volume. So if the element starts to get squished, it'll get stiff. If the element gets small, it will get stiff. That keeps the elements in good quality shape as the mesh is moved. Poisson's ratio is a dilatation parameter, and we just basically set it to a value of 0.25 and leave it at that. All this has been documented in AIAA Journal in 2007. So here you'll see a comparison of the two different meshes. The top mesh is the Pointwise GridGen hybrid mesh using T-Rex for the viscous layers, the structure block behind the club head that was manually created, and then the isotep mesh in the volume to fill the rest of the void. It's about 1.72 million points. The bottom mesh is the Pointwise V-mesh hybrid mesh. So Pointwise created the same surface mesh, and then the voxel mesh created the hex dominant volume mesh that also has the pyramids and prisms in the transition regions. And then Pointwise was used to stitch the two together, and PVLI was used to insert layers. This mesh was about 2.05 million points. The number of points is a control parameter. You can change different things and basically get the similar mesh densities. You'll notice that we didn't quite match resolution in the hex areas, and that's something that you can play with. When we go to run the flow solver, we have a code called TENASI, and it's one of your typical Reynolds average Navier-Stokes code. It does unsteady flows. It can do high speed and low speed flows. We have a preconditioner algorithm that allows us to do fully incompressible to high supersonic flows. It has implicit time evolution, point implicit with subiterations. It allows for highly stretched mixed elements, so we can do the viscous layers with meshes that are very compact and refined. And we've done Reynolds numbers for hydrodynamic cases that are in the billions. We typically get a y plus a 1 for the first grid point off the wall. TENASI is actually a framework that allows us to solve any kind of field equations. We're obviously doing fluid flow here, aerodynamics, but we can also do electromagnetics, plasmas, and other things. It is parallel, scalable, and we've run it on hundreds of processors. We have our own Linux cluster here. We have a variety of different turbulence models at our disposal, and there are some other domain-specific features that allows us to do rotating components and body forces and so on. And there is a GUI front end to set up the problem and control the run.
The flow parameters that I chose for the case were a VREF V infinity of about 4.5 meters per second. That equates to 10 miles an hour, which is roughly 1/10 of a maximum club head speed for a professional golf swing. A professional golfer will have a club head speed of about 100 miles an hour at the bottom of their downswing. Just chose a reference length of the club head depth, and that comes out to be a Reynolds number on the order of 36,000. And we used a solution scheme of variable Mach and the two-equation K epsilon, K omega turbulence model. The Pointwise mesh was run on 32 processors. It took about 6.5 hours. The voxel mesh was 64 processors, took about 4.25 hours. And the unsteady runs were computed with time steps of 1/1000th of a second, and they took about 5 CPU seconds per time step. And then 50 of the unsteady time steps were saved to FieldView files that you'll see in a few minutes. Oh, you will see now.
Okay, we're going to switch things over to Eve Marie now, so just hold on one second while we switch over to him.
Okay, thank you, Chris. So let me start first by saying a few words about the goals we had in mind when analyzing these simulation results. First, as you can see from the picture on the right here, the flow around the golf club head is quite complex, clearly very trendy and very unsteady. So we wanted to find a way to interact with it, with this transient flow, and really try to get an understanding of this complex physics. Then we could also imagine that a golf club manufacturer we'll want to do such things as reduce the drag of the head in order to reach higher speed during the swing. So for that reason, we looked into some quantitative results, the drag, its average over time, its fluctuations, as well as its distributions around the head. We could also imagine looking at various quantitative results, such as the moment around the shaft of the club, for instance, in order to study the stability of the golf club. Next, we will also wanted to be able to compare the results obtained on the two grids generated by Steve and Bruce. And the last goal is more of a methodology goal here, as we wanted to be able to save the work done on the first simulation result and reuse it for the following results in order to save time on post-processing. So before I start talking about how we achieve those goals, I also wanted to step back a little bit and say just a few words about the typical bottlenecks that we see in CFD workflows today. First, and that's especially true when working with such large transient data sets, reading or moving your files can take a lot of time. Then, if you have many designs to look at, analyzing many data sets requires repeating many steps. And those two things really cost companies a lot of engineers' time. So at Intelligent Light, we tried to come up with a CFD data management solution, and we call it XDB workflow. Here is the idea. Basically, you start from, as usual, from your raw CFD data, so that is the large 3D files you output from your solver, and you use FieldView to compute and plot your usual geometries, surfaces, streamlines that we call post-processing objects. And then the new thing is that with FieldView, you're now able to save those files into, save those objects into an extract database file, and you're also able to load it back inside of FieldView. So how does that apply to our golf club simulation? Well, we had those large transient data sets, so about 240 megabytes per step, 2 different simulations. There was about 11 gigabytes per run. We processed those large files through a FieldView batch station to generate a set of 3 XDB files, and you'll understand later why we wanted to put them to work with separate files. So we had one for just the geometry, one for some cutting planes, and one with an isosurface of vorticity. And you can see that by extracting those files, we are getting a 7-to-1 reduction in data size, which naturally brings a lot of benefits for everything that is related to touching the data after that. And I would even say that we could have had a more beneficial reduction factor if not working with isosurface, as you can see here. This is taking most of the memory of the disk space we're using just for the isosurface. So the other great thing, once you have such batch process in place, is that it is very easy to reuse it for the subsequent simulations you will be running. So for the same cost, you are getting your extract database files for the other mesh in this case. So now that we've got that in place, let's look at the actual post-processing that we did with it. So remember that I told you we wanted first to look at the transient flow and try to get an understanding of it by really interacting with the data. So we loaded in FieldView session just one time step of the golf club geometry, since this one isn't changing at all. And we also added to it the full time steps for the isosurface. Once this is loaded in FieldView, even on a very reasonable system like my laptop, we're able to get a frame rate of about 18 frames per second when interacting with the transient dataset. So let me try to show you that quickly in FieldView over here. So I got my extract datasets loaded, and once I have that in memory, I can very easily change from one type step to the other. And as you can see, this is happening very fast. I can also change view, rotate, zoom in over here. And the great thing is that I can also do both at the same time. That is, animate the results and change the view. Well, I need to apologize since I guess that on your hand, due to the low frame rate we have through this GoToMeeting application, you're not really getting a feeling about my 18 frames per second. But if you have a chance to try that in FieldView, you will really see what I mean with this high frame rate. Okay, so let me go back to the rest of my slide over here. So once you've gained such an understanding of the complex flow physics, if you want to share that result through, for instance, AVI animations, the great benefit that you have when working with extract like that is that you also get a speed up for generating those animations. So in this case, it was a 6x speed up. That means that in the same amount of time, I was able to generate 6 times as many animations, let's say 6 different views, or work on 6 different colors for the cutting planes, and so on. So next, we wanted again to work with 2 datasets at a time and be able to compare them interactively. So what we did was to load our 2 extracts containing the cutting planes. And once you've done that, it's very easy to put together a view where you can recompare the shading that is happening on the 2 simulation results, depending on the grid that has been used. And since you're getting a great 28x speed up for loading your data, it's then very easy to go through your different time steps. We also wanted to be able to do some quantitative analysis and comparison, which takes an additional interpolation step. And this interpolation used to take a lot of time when doing it on full 3D datasets. Well, the great benefit here is that by working on just some planes that you choose, you can it can come down to a much smaller time. For instance, here it took only about a second per time step to interpolate those 2 cutting planes, and that gives us a great speed up for looking again at all the time steps and comparing the results quantitatively. As you can see over here, we are looking at the difference between the 2 velocities computed on the 2 different grids, which clearly highlights some areas of discrepancies. Last, I also told you we were interested into looking at the drag. So what we did in another FieldView session was to load just the geometry with the pressure information on it and run that through a FieldView program. So FieldView is FieldView's programming language. This program was able to take small slices of the golf club going along the lens, and for each one of those slices, integrate the pressure drags, sum that to get the distribution, and also do that loop and that integration in slices over time, and send that into Excel ready sheets. So with that, we're able to get some plots like this one, where we have with this black line the time average value of the pressure drag distribution, as well as the minimum and maximum for each one of the slices. And that kind of plot brings a lot of information. For instance, we can see that most of the fluctuations are happening on the rear part of the golf club head, which is really no surprise because that's where the shading is happening. We could also look closer at the plot to try to figure out at which locations the design could be improved. And again, the great benefit when working on such a script with extract database is that it takes far less time to debug the script, to test it, and then have it run on your data. Okay, so with that, I'm done with the post-processing part, so I'll get back to you for the summary.
Okay, I'll provide a summary of what we've shown today. Basically, we've taken a analysis of a golf club head and used it to demonstrate a complete safety process. That involved doing some geometry creation outside of GridGen and Pointwise and plus inside GridGen, and then doing the meshing within Pointwise and another code, and then all the way through flow solution and post-processing. And as we pointed out, we used both Pointwise and GridGen for making one version of a viscous mesh, T-Rex in the GridGen version. And then Pointwise was very flexible and allowed us to use our own tools, vMesh and PVLI, to create a second version of a hybrid viscous mesh. Next slide, please. And we did both steady and unsteady solutions for one flow condition on our Linux cluster here at the SimCenter. And the results were then written to files and then post-processed, and Eve Marie showed an excellent comparison of the results from the two different grids and what capabilities are in the FieldView product. This is a typical analysis process. Many of the steps that we showed you here could be automated through scripting for like configurations and topologies. And we could also do geometry changes, and we can incorporate them in doing some improvements to the club head design. And we didn't show any mesh adaptation, but we could also include that with the vMesh or voxel mesh version of the grid. I think with that, we'll go to the next slide and take some questions and try to answer them for you.
All right, thanks, Steve. So thank you, everybody, for your attention on the webinar today. Just a little bit of information about what's going to happen from here on in. We'll move to the Q&A session right now. Before the drill, just point out that this webinar will be available for viewing later on the respective URLs you see on our website as well as Intelligent Light's website. So if you have any questions about anything to do with Pointwise or the pre-processing you saw, feel free to email me directly, again, on the post-processing. Any questions you saw and you got questions about what you saw here today, go ahead and email Eve Marie. Or just in general, if you got more questions about what we saw in the actual application, it's probably best to touch base with Steve and Bruce, and their contact information is here as well. So with that, I'm gonna open up the floor to questions right now. So how it'll work is I'll moderate the questions, so go ahead and type those in to the Q&A panel in your little GoToMeeting navigation panel, and then I'll assign them to the appropriate person. So here we have a good one from Jason Mateer. I think this will be a good one for Steve and Bruce to answer. His question is, with today's solvers, does it really make that much of a difference to resolving vortices if we have a TET versus block structured mesh, assuming we have about the same grid spacing in that region?
Well, our experience is definitely yes. The difference between if you have an all TET mesh in a highly active region and you have an all hexahedral mesh, it makes a really big difference, especially in applications like turbomachinery or when you're calculating drag, like we were on the golf club. So I would say yes.
Another example is if you take a surface ship and there's a sonar dome in the front bulbous section of the ship. If you use an all-TET mesh behind that bulbous region and downstream, you will dissipate the vortices almost immediately. But Bruce has actually learned how to create blocks of structured meshes in there, and it retains the vortices and tracks it more accurately downstream. So it is definitely important.
Okay, thanks. So we have a question for Harris Hamid. He says, hi, what geometry changes for the golf club head would you recommend carrying out after a detailed CFD analysis? So, I mean, I guess I'll let, again, Steve and Bruce go ahead and answer this question.
Well, actually, we would let our flow solver make that decision for us. We have the ability through adjoint information to prescribe changes to the geometry. It depends on how it's defined. We will actually couple it with a CAD package and drive the change in the geometry from sensitivity analysis of the solution. We'll ask the flow solver questions like, how can I make a shape change that's going to reduce the drag on the golf club? And it will tell us in regions of the golf club head where we need to make changes in what direction. So we're going to let the methods tell us where to do that.
Okay, good answer. Thanks, Steve. So I have a question here for Eve Marie. What are the limitations of the XDB storage? Can it be used for streamlines, for example?
Yeah, it can be used for all the post-processing objects that you typically create when working in FieldView. So you could put streamlines in it, isosurfaces, cutting planes. You could also put some particles in it, but for performance reasons, we recommend to keep them separate in a FieldView particle path format. So yeah, really I will say no limitation. All of the objects that we handle in FieldView can be saved into those files.
Okay, thank you, Eve Marie. So just a question here about Pointwise. I'll go ahead and answer this one. It says, this is from Lakshmana. Does Pointwise have an integrated voxel mesh module? No, there's not a direct coupling, but part of what Steve and Bruce were showing is that it, through some of the flexibility in the formats that Pointwise supports, it's very easy to couple. You know, it's seemingly two very distinct meshing approaches, but because voxel mesh requires a triangulated surface mesh to begin with, and he's able to do that fairly easily in Pointwise as well. And the application he was showing was fairly simple. It was just a sphere, but you can imagine a much more complicated case where you maybe need some sort of CAD tools and some extra facilities for being able to create a little bit more complex triangulated surface mesh that he can provide to voxel mesh. All right, maybe another one for Steve and Bruce here. It says, this is from Chandan Kumar. For geometry cleaning, how many iterations did it take you to clean up the model?
I'm not sure what you mean by iterations, but once we got from our CAD package or the cleanup software, the fairly poor quality geometry with the holes in it, it didn't take me very long just because of my experience to go in and say, oh, well, let me put something over these holes. So there were, I guess there was one iteration, if that's the question.
Okay, thanks, Bruce. Probably another one for Steve and Bruce here. Just a general question about CFD and golf club design. Do manufacturers do wind tunnel testing on new clubs to ever get validation of these models?
Beats me.
I don't know. We haven't talked to any manufacturers, but I believe they probably do, at some level, do some CFD analysis. I don't know that they go to the high fidelity that we're talking about here. We used a Linux cluster, and not too many people have access to that type of compute power.
Okay. Okay, there's a question I'll probably answer here. This is kind of related to both Pointwise and FieldView, but this is from, can we use the Pointwise license for pre and post also, or do I need another also? Yes, I mean, they're separate and distinct products, so you would have to get your own license for each application, yes. Let's see, let's look down the list of questions, what we got queued up. Okay. So just a follow-up from Chandan Kumar, the cleaning process, how many, he's asking maybe more specifically, how many operations did it take to actually clean up the model, like filling the holes, stitching meshes together, repairing missing geometry, et cetera, et cetera?
After it got into Pointwise, not a lot. I believe I put 2 structured patches that I then converted into database or geometry elements, and just made sure they were smooth with the existing geometry that had come from the laser scanner post-processing package.
Okay, thanks, Bruce. Here's another good one for Steve and Bruce. This is just a follow-on to Jason Mateer's original question. I assume when you calculate drag, you integrate pressures and viscous forces over the golf club head. Does resolving the vortices downstream have a measurable impact on this integrated drag? I can I can see maybe on a ship it would have an impact because of the length of the ship and the interaction, but for the golf club head?
Actually, it is important because we're talking about a flow field that is an elliptic in mathematical nature. So things that happen downstream do actually affect things upstream. If it was supersonic, that wouldn't be the case, but in this case, it's definitely subsonic. So there is an effect on the wake on the golf club itself. And when we would do an analysis like this, we would actually compute the complete drag, pressure plus viscous. Eve Marie just looked at the pressure drag. So we would actually look at all components.
Good. Thanks, Steve. Just a quick one about Pointwise here. Does Pointwise version 16.04R4, which is our current production release, contain the T-Rex 3D meshing feature? No, it does not. It contains the 2D T-Rex meshing feature, but not the 3D. As I mentioned early on in the webinar, Pointwise version 17, which we're working on doing some internal beta testing right now, we're hoping to get it out in the early new year, will have the full 3D T-Rex capabilities that Gridgen has, actually plus a little bit more. So you'll definitely want to keep an eye on our website early in the new year for some information about webinars and some informational material on Pointwise version 17. Again, I think this is another question here for maybe Steve and Bruce from Harris Hamid. How do you go about selecting the size of the structured block for capturing the wake?
Experience, basically. I mean, I will put as many hex cells behind an object as I think I can get away with in terms of point count. I probably could have done a lot more in this case because we only had a 2 million point grid, which we have the capability to handle, but I just said, this is about right.
Plus, once you have a solution in hand, you can actually post-process it and figure out whether you captured it adequately or not, and then go back and do a remesh and do it again.
So maybe I'll just add on a little bit to that. Can you maybe comment on maybe roughly, like, I mean, at least as an initial guess, let's say how many club head lengths downstream would you, as a first guess, make the length of that wake block?
I'm not sure what I did here, but typically I would think somewhere in the neighborhood of 3 body lengths it's usually adequate.
Okay. All right, we have another add-on question. This is from Brad Johnson. He asked the question about using CFD on golf club heads from manufacturers. He said, is CFD in high demand from golf club designers, and have you ever done any other clubs besides a driver?
We have not. We actually had a student over this last summer did a flow solution over a dimpled golf ball, so we're thinking about combining the two, have an impact of a golf club head with a golf ball. Cool.
Let's see, I'm just looking at a couple more questions kind of come in here. Maybe take a look at them. Okay, we have a question for Srinivas. Is the final grid seen in this study an economic one? I mean, did you do a grid refinement study to get similar results with a grid with less number of cells or points?
No, we did not. We're negligent in that regard. Typically, the question refers to do you have a grid convert solution? So you do one grid, compute a solution, refine it, and see if the solution changed until you reached a point where you had grid convergence. The solution did not change. We did not do that in this case.
Okay, another question from Chanda about the meshing in general. Is the meshing done by selecting the whole model and defining the element size, or the grid for the golf club head, or by assigning different element sizes at different regions?
Largely, I assign the same element size over the entire golf club head, just because that was simple. I knew what resolution I needed to capture the geometry, and so I just said, make everything this size, and I forget off the top of my head what that was.
And the voxel mesh code will key off of the size of the triangles on the surface for the volume elements.
Okay. We have another question here from Yi Liang Chun. What do you think might be the reason for the difference of the two simulations, so the solver or the mesh?
That's a subject for further study. We need to do a grid refinement study. I mean, there's a difference in the viscous layers that is generated by T-Rex versus the PVLI. And it has to do with, PVLI is going to only insert layers that go to a point that matches the size of the cubes near the surface. So we had cubes that were small enough there that it didn't want to insert any more layers. So that's something that we should probably do more of in the next study, is vary the way that the viscous layers were generated between the two methods and see how that affects the answers.
Okay, thanks, Steve and Bruce. Questions are kind of winding down. I got one more here. I think I'll probably field that last question. And this one's probably for Steve and Bruce. Does the volume mesher decide by itself where to assign more number of mesh to capture the data?
As I just said a little while ago, it keys off of the size of the surface triangles to make the volume mesh. And then there are some parameters on how many cubes of a given size do you want before transitioning to a coarser element. So there's a jump there in size of 2 to 1 when it transitions. So those are parameters that the user has. In addition, when we do adaptation, we will take a CFD solution, actually read a FieldView file, and post-process it through a code that will generate a spacing field that keys off of gradients of some selected function like Mockman curvature. And then that tells voxel mesh in the next iteration where to refine the grid to further resolve gradients in the flow.
Okay.
I might add, you can also define rectangular regions where you want to force voxel mesh to refine down to a certain level. And that's what I did for the wake behind the golf club. If you look at the picture, the voxel mesh picture, you'll see that there's an obvious place behind the golf club head where the voxels were kept at a certain size. And that was as simple as defining a rectangular region in space.
Okay, I think we're getting pretty close to the end of our time. I think I'm going to field one last question that's kind of a little bit more related to the solver. So this again will be Steve and Bruce can handle this one. This is from Vladimir Yumashev. Computational times look relatively low as compared to our experience despite the number used. So that's more of a comment than a question. So maybe I'll just let you guys just kind of fill it, maybe add a little more to that comment.
Well, again, we're using parallel processing, and our code is very efficient and highly scalable. So it's just, I guess we've achieved some pretty good efficiency in the flow solver. If you've got specific questions about the flow solver, you can email me and I will direct it to our solver developers.
Just one, I'll just add on a little bit. Steve, can you comment on the availability to TENASI? Is that just an in-house code for use for UTC SimCenter users, or I mean, how does it work there?
We have used it on contracts and such. We're not actively promoting it as far as commercializing, but there are instances that we might consider it.
Okay, very good. I think, yeah, again, we're a little over on our allotted time of an hour, so I want to thank everybody again for their time today and all the questions and your attention. So thanks again, and I look forward to recording this webinar on our respective websites tomorrow, and also future webinars down the road. So thank you very much.